You know, being sandwiched between Jeff White and Edward Snowden, just life goal ticked, you know, for sure. And you can't often say that, I think. So I think the secondary title for my presentation really is, let's have a frank conversation about AI. And what I'd like to do, if I may, I'll confuse the issue of some facts, which is always a dangerous thing to do. And first of all, here's my detail. So as a South African, I feel deeply inadequate by the number of followers that Elon Musk has. So I'm trying to catch up, but I suspect my wife and two daughters not going to help me much in that regard. So here's my detail. You know, there's some interesting conversations on Twitter, so do follow me. Now, in my presentation, I don't want to use tired imagery. You know, we're so used to the hooded hacker, the robot staring into space thoughtfully. You know, none of those. I thought I'd have imagery that makes sense to me as a South African. So I've got some Zulus, as you do. I've got some zombies. I like zombie movies. And I've got my local gym I go to, the Ironworks gym. And I've got those three images in my presentation. I'll weave them into my story. So let's start off. Now, first of all, this is quite an ambitious talk, and I won't make any apologies for that. You know, I'm trying to convey some complicated concepts in 15 minutes or so. But I do want to do it in a thorough, rigorous way. So not talking generalisms, want to talk about specifics. So let's take the journey. So first of all, the one thing that I stopped getting annoyed about is this interchangeable use between AI and ML, machine learning and AI. You know, I think AI is a marketing term, but let's look at the proper definition of artificial intelligence. For something to be artificially intelligent, it needs to be an agent that's got the ability to sense its environment. It then uses algorithms, most often machine learning algorithms, to maximize its success function. So if you're a self-driving car, you've got LiDAR, you've got radar, you've got photos, and what you will do is you use machine learning algorithms to use that information to maximize your success function, which might be to get from point A to B legally and safely. That's AI. So for it to be AI, it needs to have the ability to make decisions and maximize the success function. Now, certainly in cybersecurity, there's no implementations of AI as far as I'm aware, not even on the offensive side. What there is, however, is quite a lot of machine learning. And this talk will really concentrate on machine learning and a little bit of deep learning, just because deep learning is like the dark web. You know, it sounds complicated and deep and powerful, and it's fantastic. So I'll talk a little bit about those two areas, but in particular around cybersecurity. Now, so first thing is, you know, when practitioners talk about machine learning, they'll talk about loads of algorithms. Now, on the left-hand side here, you can see there's a number of algorithms, but broadly, it breaks down into two types of algorithms, supervised learning and unsupervised. So supervised, what I have is I've got labeled data, and lots of it. The key thing is, if I'm trying to predict whether the data will be malicious or not, what I do is I take an algorithm, I tune the parameters of the algorithm, given the data that I've got, to predict whether something's malicious or not when it gets new data in the future. Okay, so all it is, mathematical model, and I use lots of data to tune the parameters to predict something in the future. Now, for this to work, I need to have about an equal amount of good data or bad data. So if I'm trying to predict if something's malicious or not malicious, I need to have about the same amount of malicious data and not malicious data. Okay, and I'll get onto that in a minute. The next type of algorithm is unsupervised. Here, I don't have lots of training data. I just have data. And I'm trying to determine some structure in the data. So I might have a lot of log files, log entries, and I'm trying to see which of those log entries indicate that somebody is behaving differently to the rest of the users. So a lot of traffic into my website, I want to figure out which ones are different. So I'm trying to determine structure. Now, in cybersecurity, this is the most common way that people will apply machine learning. Okay, now, so talking about supervised learning. As I said already, a couple of key things. I need training data that's labeled, and the training data needs to look like the data that I'll see in future, and I need about equal amounts. But here's the thing. Most of the current crop of machine learning algorithms gets trained by the following data sets. Okay? DARPA 1998. You know, then we've got the KDD 1999, which is a bit more current. Then you've got the ISC 2012, and if you're really lucky, there's a data set ATFA 2013. Now, guys, come on. 1998, that's before the bloody internet. Yet we're training machine learning algorithms to detect suspicious and anomalous behavior using these old data sets. And now if you think again about the thing that I said before, which is that for this to work, for this model to accurately predict malicious or not malicious, the data that it sees needs to look the same as the data it was trained on. Right, okay. Wonder how that's going to work out. So key thing here, supervised learning. Now, a common example of supervised learning will be a neural net or deep learning. And I'll give you an example here, not cybersecurity related, but it looks cool, which is how does a self-driving car recognize what different things are? It uses something called deep learning. Now, deep learning sounds complicated and fantastic and powerful, and it is kind of, but all it really is, in this instance, you break a picture up into a bunch of pixels, red, green, and blue, which have values, and there's a bunch of matrix multiplications. And what I do is I take hundreds of thousands of pictures, I tell it this is a car, and it will then figure out how much weight it should put in each of these layers. So what the convolution layer will do, it will take a little filter, which is trying to detect features in the picture that is a good differentiator to predict that something is a car or a truck or a horse or whatever the case might be. And you can see here, it kind of looks like a car. The activation layers figure out which of those ones are important, and then you keep doing that until you get to quite a good predictor of being a car. And these things are very common and are used quite a lot in machine learning. Now, the reason I've introduced this is that I'll introduce a practical use of deep learning in cybersecurity a little bit later. So just keep that in the back of the mind. So now the next algorithm I want to talk about is unsupervised learning. So with unsupervised, as I said again, we don't have labels. I just have data, and I'm trying to figure out structure in the data. Okay? As an example, typically for us, a lot of log data, and I'm trying to figure out which of the log data is malicious, which ones is not, or which logs is different to the other ones. Okay? So now there's two approaches to figuring out what the structure in the data is, and I'll explain why I differentiate the two. Now, this is quite an advanced concept. The first is called discriminative. And here, I don't assume the data was generated using any mathematical model. I just assume I want to see what the structure of the data is. And the second approach is I'm assuming the data was generated using a mathematical function. Now, in cybersecurity, generative models get used the most because mathematically they're convenient. And they kind of almost make up for deficiency in labels, because if you can assume there's some structure to the data that I see, you can then say, okay, well, this doesn't look like other data from that mathematical function, must be anomalous. I'll talk about that a little bit later. Let's make a drill. Okay, so the first model is discriminative, and what I've got here is a very simple, simplified model, but it's real data. On the one axis here, I've got number of pages that somebody visited on my website, and here's how long on average they stayed on each page. Okay, so you can see, as a human machine learner, it's quite clear. There's 4 clusters there. This machine learning lark is quite easy, you know. So how on earth, however, does the algorithm figure out these 4 clusters? And how does it figure out which points belong to which cluster? So an algorithm we're going to use here is k-means clustering. It's very simple. What it basically will do, it will choose 4 random centers, and then say which points are closest to these random centers, and then it will go to the middle of the points assigned to it and keep iterating over this. It makes more sense when you look at it. There we go. So I've got my 4 random points, goes to the center of those points, assigns the closest points to that, then go to the center, and it'll keep iterating. You'll see pretty soon it will converge, and it's quite accurately predicted which points are closest to each other. Okay? So that's how unsupervised learning using a discriminative model will work. Now, some of you may wonder in the audience, how do you decide how many clusters to use? That's a good question, by the way. There's principled ways of figuring it out, which is beyond this talk. But in principle, that's unsupervised learning, and that's how I might do it. Now, let's look at a more complicated version of that, which is a generative model. But before I do that, I need to introduce my little Zulu here. You know, it's a beautiful picture. I love that picture. It's really so proud and regal and everything else. Why do I introduce him? Because I want to talk about a Gaussian. What is a Gaussian? People might think of a Gaussian or heard of a Gaussian as a normal distribution, a bell curve. And what it basically says is that most data is close to the average, and as you get away from the average, you can predict how much of the data will be at certain points. So it's a very simple thing to do. Why do we use it in machine learning? Because if I integrate it as a nice little function, it's beautiful. If I differentiate, it's the same thing. So mathematically, it's quite convenient. But the other reason we use it is because actually it's quite common in practice. This is my gym, the Ironworks. Now, the owner always asks me, why the hell do you take a photo of my oldest piece of equipment? But the reason I did is if you actually look at this spin stack machine, most of the people go to the middle. You know, actually, this is a Gaussian distribution. Now, for the record, I'm a top of the stack kind of guy. The guys I'm extremely afraid of are the bottom of the stack, but most people are the middle of the stack. So it's quite common in nature, Gaussians. That kind of happens, okay? So now, the same example of classifying the points. Let's look at using a generative model. And what I'm going to do here, I'm going to assume that each of these clusters was generated using a Gaussian. And effectively, that basically says most of the points are close to the center, okay? And how am I going to do it? I'm going to start at 4 random Gaussians, and then say how likely are the points to be generated by those Gaussians, and then I'm going to update my Gaussians based on the likelihood. And there we go. You'll see in a minute. Or not. There we are. And you'll see after the little 20-second animation, I get the same clusters that I got with my discriminative model. And there we are. Except with this one, it's a bit nicer because actually it's not quite so binary because those points could belong to that cluster or that cluster. So it's actually mathematically more accurate. Okay? So now most machine learning algorithms that you see today they use hushed words, recursive Bayesian estimators, advanced math. We'll use generative models and assume the data is generated using these functions and then tell you if any of the data is different to the previous data it's seen. Okay? So which is why I introduced the use of concepts. So, which gets me to my point. So all this AI and ML lark is going to protect us, all right? I should be sitting on the beach in the Bahamas. Not be presenting here, well, before Snowden, that's fine. I'll do that any day. Any day. But, so how come we're still doing this stuff if AI is going to protect us? The reality is that most of the current deployments are just deployed in the wrong place. They're just not effective. And that's a big statement, guys. That's a really big statement I'm making here. And I'm very conscious of my statement. Why do I say that? First of all, if I look at the world, it took me some time to create some Zulu icons, which I quite enjoyed. It's the first, I think. I don't think there's a lot of other Zulu icons about. So I've got my attacker. He's frowny face, must be a bad guy. He's going to get those users. My users are all friendly and nice, okay? I've got my defender. He's got his little leopard skin band on, so he must be good, okay? And what do the attackers do? The attackers trying to phish my users. They're trying to traverse the network, find bugs. They want to persist. That's what the attackers do. The defenders, on the other hand, educate the users. They provide, defensible networks, safe defaults, authorization, access control. They do these things to help my users being protected against these pesky hackers. Now, the reality is the hackers are trying to evade the detectors, and the detectors or the defenders are trying to detect the attackers, okay? So now going back to my definition of machine learning, the data needs to look the same. The data that I train my model with needs to look the same as the data we'll encounter later on, or else it won't work. Now think about it. My user's behavior doesn't change. Yet my attacker behavior changes. Attackers change their modus operandi depending on what happens. So actually, if you think about it from a machine learning point of view, the worst place to deploy machine learning is in that detection capability. Why? Because by definition, the data is not going to look the same that I trained it with as what the attackers will do. It's more suited to actually attackers, because I can train their models in how users behave, and they know that's going to be accurate. So, next step. So this just summarizes what I just said there. Let's see what the time is. Okay, good. We're 5 minutes, okay? So now, basically what I've been saying here is that the current state of affairs is flawed, okay? Most machine learning algorithms are glorified anomaly detection, really, okay? And it needs a lot of training data, which we don't have, and if it uses a generative model, that doesn't reflect attackers. And this little cartoon summarizes that perfectly. If you read that, basically it's somebody saying, well, our system learns of your network. Oh, so it's changed detection. No, it's not change detection, it's cybersecurity. But hang on, so how does it know the difference between attack and change? Well, actually we don't. And that, unfortunately, is the reality of the current state of play. So how do we do this better, okay? We use it as a tool, not as a solution. And I'm going to give you 2 very quick examples. One is to detect CNC traffic, and CNC traffic is command and control traffic. And what happens here is somebody compromises the endpoint. This endpoint will try to speak out on the internet to a server which will control it. And how do I detect this? I detect this because generally these CNC servers will use a long random name. So you can't block it. The name will keep changing. because if it doesn't change, people will just simply block those command and control servers and their firewalls. Okay? So how do I do that? I use a deep learning, I use a neural net, a LSTM, and how do I train my neural net? I first of all take families of malware variants, about 1 million of them, 100,000 of each, and I effectively teach this neural net with the sequence of characters, which sequences of characters are bad. It's quite easy for me to get good data because I can look at the Alexa million. I can look at the million most common websites, Netflix and Amazon and those things. So effectively what I've done here is I've trained a neural net what sequence of characters will normally be bad and which ones will be good. Okay? Very simple application, very specific. And so effectively what now happens when a compromised machine tries to make a connection to the CNC, it will do a DNS request to connect to the IP address, and we are capturing these DNS requests and analyzing them in real time. And again, you see a result here of that. So what you see here, as a human machine learner, you can clearly see that that name is extremely random, must be malicious. But the point is, we did this using machine learning. That's not a name we trained it with. It just follows a similar sequence to other ones we trained it with. That's all. Now, the next one, which is more interesting for me in the last 3 minutes I've got, is analyzing large volumes of log data. And this is where my zombie will come in a minute. So what I really want to do is, I want to be able to analyze 25,000 log entries. Now, for typical customers, how many log entries you'll get from your endpoints? Now, 25,000 is far too much to focus on. When you have 25,000 things that are suspicious, then nothing is suspicious. So the question is, how do I figure out which ones of those are interesting? And so here's the example. So I've just got all my endpoints creating sysmon entries, which ends up in an event log. Now, what I'd like to do, actually, is to say which of those log entries are similar to each other. I want to do some form of clustering, as I showed you earlier. I want to say, of those 25,000, those 2,000 look the same, those 100 are the same, those 400 are the same. And I want to have my analyst tell me which log entries I care about. And this is where the random walk comes into it. So what my guys do, we've got about 102 here. They look at each of those log entries and they classify them to say, this is suspicious, this is normal, this is GoToMeeting, this is Excel launching external file. And what I now want to do is I want to say, of my 25,000, like which of these 102 they look like. So they can only focus on the ones that really matter. And to do that, I use, here's my zombie, in case you're wondering, zombie eventually came up. And the reason I call it the zombie in here, this thing is called a Markov chain random walk classifier, sometimes called the drunken walk, but I prefer zombie, because zombies also stagger, okay? And how this thing will work, if you look here, my guys have labeled 3 log entries, and it's going to start, let's say it wants to classify this one. It's going to walk, till it reaches a labeled point. Then it knows that that's the same type as that. Now, if you think of my example of K means clustering I showed you, that would not work, because that would think that these are all similar to each other. No, they're not. You can clearly see there's 3 families of log entries here. Okay? So let me show you that in practice. And you'll start seeing that some of these points get labeled because it will keep walking. Now, obviously, the more points there are, the quicker it labels them, because it gets to a similar point a lot quicker. Okay? And we are. They're all labeled. So this is only with 3 labels, okay? Now, if I had 102 labels, I would have had a label here, there, so it'll be, there'll be a lot more colors, but it's just to illustrate the concept. The point I'm trying to make here is that this is using it as a tool in a very specific way, solving a very specific problem. Not saying broadly we can solve your cybersecurity issues. And I guess just to show the results here, so here's a log entry at the top that was one of those labels. And what the classifier picked up, it picked up these 28 other entries are similar to that one entry. And the point here, what was here is Excel connecting out on the internet, downloading a file, running it locally. And I want to find out where else this happens. Now, as it happens, I'm one of the other ones that behave similarly. And in this case, it was me connecting to a DNS host on the internet. It was Google, so it was fine. So it was not an issue. But the point being that we only had to analyze 28 entries, not 25,000 entries, to find that those, and we can deal with 28 entries. So my key takeaways, and this is on me concluding just on the half an hour. The first thing is, I think machine learning will make a big difference in cybersecurity and our industry. I think it is important to at least have executive level understanding of the stuff, or to have somebody within the organization that does, because it will change the way that we operate in this space. It's important to ask the right questions of your suppliers. When people make bold claims, we solve your cybersecurity issues. No, I'm sure it does not. What exactly does it do, and how does it do it? Then the next question to ask is, how many anomalies will I get? How many alerts will I get? How many do I have to deal with? And be skeptical about very wild claims. guys, and ultimately, I guess it's I think it's important to get somebody in the business that actually has some understanding or partner with somebody that does. And on that note, that's me. Here's my Twitter handle again, and thanks for your attention. Thank you.